here to talk about compile time built-ins in Wasmtime. So what are compile time built-ins? These are basically a mechanism to allow hosts to implement their own host APIs as WASM components instead of the traditional way of using like linker, func or etc. So this is kind of like a niche instance of the general technique called self-hosting. And then, fair warning, this is all still a bit of a work in progress, not necessarily production ready yet. So tread carefully. So let's jump into an example. So here we have a WASM guest. It's a component. It imports a +1 function. Uh, and so here's kind of the traditional way that you would implement this on the host. You'd have a linker, and then you would, register a function under the name +1, and it would take, some value and return that value +1, right? Boring. More fun is compile time built-ins. And so with this, you can attach these to the code that you're compiling, like to the component that is being compiled or whatever. And you say register a compile time built-in, and you provide a component. And this component should export, something that matches your host API. So in this case, +1, there's a bunch of like lifting, instantiation, whatever stuff going on. But this middle part here, I32 add local get 0, I32 const 1, it's adding 1. All right. So why go through all this rigmarole? What's the big deal? Well, this enables function inlining for your host APIs. So this means that there's no function call overhead from the WASM guest to your host APIs, which by itself is a little bit of a win, but it's not that much. But the big thing is that it unlocks further optimizations kind of based on the call site and the actual arguments and things like that. So for example, calling some objects getter method, which maybe has like an assertion that, something is non-zero or whatever, right? Just becomes a simple field load because the assertion was able to like be statically removed by the optimizer or whatever. If you want to learn more about like all the stuff that function inliners can do, I wrote this article, go read it. So the next thing you might be thinking though is like, oh, my host APIs, the reason they're host APIs is that they need access to host data. Well, we expose to compile time built-ins this thing we call unsafe intrinsics. These are things that look like function calls at the WASM level, but when we compile the WASM, we're actually translating those things into raw inline operations. So these are, loading native loads and native stores, in the endianness of the target, and just raw U8 load with no, bounds checks, no nothing, no safety wheels. So it's kind of up to you to respect the host language's kind of memory model and aliasing model and all that stuff. And then sort of to kind of like root your initial data access, there's also an intrinsic called store data address, which gives you the address of the T in your Wasmtime store T. So this is an incredibly sharp knife. It's very powerful. You can do arbitrary stuff, right? Any kinds of native loads and stores outside the sandbox, whatever. And it's also very dangerous. So preserving the sandbox and safety properties and all that stuff in general is your responsibility. You must ensure that your compile time built-ins are memory safe. They don't expose private data from one guest to another guest or the host's private data to the guest. You need to make sure that they're free of denial of service attack vectors, all of that stuff. And you have to do this for all possible inputs. This includes like when the guest is incorrect and gives you invalid arguments, or completely random data. Like you still need to be robust in the face of that kind of stuff. So yeah, you implement bounds checks, whatever else you need to do in your compile time built-ins before forwarding arguments into unsafe intrinsics. And kind of the rule of thumb is to always assume that the WASM guest is malicious. But kind of the good news, I don't know if it's good news, but Interestingly, this is actually no different from traditional host API implementation. You can write sandbox escape bugs with traditional host APIs the same way as if you incorrectly exposed unsafe intrinsics directly to the guest. And so here we have, exposing an arbitrary read function, which takes a integer, casts it to a pointer, and then just does a load. Right? Um, so yeah, what's kind of the holy grail we're aiming for here? Ideally, we'd like to have zero copy and zero function call overhead host buffer access. This is something that people have wanted a lot for kind of the component model and all that stuff, and I believe this is a way to do that. So if we start with the host code, uh, we need to make sure that everything we expose to WASM has kind of known offsets. And so we have repr here. And additionally, if you want your code to be portable, then you need to make sure that the size and offsets are going to be consistent across 32-bit and 64-bit architectures. And so that's why we have this sort of U64 padding going on right here. This is very similar to writing the like VM data structures inside Wasmtime itself, like VM context and all that stuff. And then, so yeah, we can assert our properties so that our code won't even compile if we're on some weird architecture where, this stuff would be unsafe. And we can create a pointer and get the pointer, whatever. And then we can pair a pointer with a length, and that is a slice or, an owned buffer. And again, we have assertions. The extra important ones here are the offset of assertions, because these are the things that our compile time built-ins will hard code these offsets into the code. So if these are wrong, stuff's going to be really bad. And creating one from an iterator of bytes, whatever, it just creates, a box U8 and then kind of pulls the parts apart and puts them into their places. And then drop, it just puts it back together to drop the slice, whatever. And then, we also have a little bit of unsafe code to like, get them as, borrows, mutable or immutable. And then, so here's where we start to get kind of interesting again. So this is creating, a Wasmtime engine and creating a store, and then we pass an exposed buff to as the T in the store T. It's our user data. All right, so now let's look at the host implementation of the compile time built-in in WASM. So the first thing it's going to do is, it's a component, and it's going to import unsafe intrinsics. So these are, all the really unsafe operations. So getting the store's data address, doing, native loads and native stores. And so we'll define a helper that gives us the pointer to the exposed buff. And so this calls store data address, and it adds 0 because it is the thing itself. We could remove that. The optimizer will do it for us. And then len is the same. We've hard-coded 8 because that was the offset before, right? But these are, kind of unsafe, right? So we need a bounds check. And so what this will do is this will check that the given parameter I is in bounds of the buffer's length. And if so, then it will return and do nothing. And if it's out of bounds, then it's going to trap, because continuing would be unsafe. And then what we do is we kind of tie everything together and expose a safe API by first doing a bounds check and then doing, the unsafe native load, whatever. And then set is similar, but instead of a load, we're doing a store, right? And then, yeah, we can also expose len. We could have exposed the underlying thing directly. Doesn't really matter. So now let's look at a guest program that uses this host buffer API. So it's going to be a component, and it imports an instance of the host buffer API, which has, get, set, and len functions. These are kind of the safe functions that we just defined. And it has a main function that's going to loop over every byte in the buffer, and it's just going to increment each byte. I don't really feel the need to step through each instruction here, but it's doing a loop. It's incrementing every byte in the buffer. So it does a load of the ith byte, and then it adds one to that, and then it stores it back to the ith byte in the buffer. Yeah, so let's look at the benchmark results of incrementing every byte in a buffer via the zero copy host buffer API with compile time built-ins, or the traditional way with linker func And it turns out that linker func is faster than compile time built-ins. Compile time built-ins are like 3 point something slower. What the hell is going on? So it turns out the component model async stuff has lots of state manipulation, and all of that is implemented in Rust right now. And so when we have component-to-component adapters, every call will actually call out to Rust twice, once at the start of the call and then once at the end of the call. And so by switching to kind of component-to-component adapters and inlining those things, we actually doubled the number of WASM to Rust calls happening. Instead of one call out to, the linker, we've turned it into a call out to like do a little bit of state manipulation and then do the inline thing and then do another little bit of state manipulation and then return. So hopefully in the fullness of time, this stuff can be implemented inline, and then we wouldn't have these extra calls happening. But right now we can just disable component model async because we're not using it here. Additionally, we defined a bunch of little helpers, right, in our compile time built-ins module, and then they called each other and all that stuff. But by default, we won't inline any functions within the same module because Wasmtime assumes that the producer of the WASM already did the beneficial inlining in kind of the scope of what it could see in the module, right? Which is going to be true if you're using like LLVM or whatever, right? But because we wrote WAT by hand, that's not the case. So we can enable this flag that just does a little bit of extra inlining, and that'll help. And so after that, we can see that things are a lot better. So ultimately, we are 64% or 64 times faster than linker func when using compile time built-ins and disabling component model concurrency and enabling intramodule inlining. Oh, by the way, this is normalized time, so lower is better, and 1 is sort of like the benchmark of what we're comparing against. Yeah. So maybe, if you're using linker func, you wouldn't actually like do this kind of, zero copy host buffer API because, it's easier to just take and return a list U8. That's sort of the more natural thing to do in the component model today. So let's also compare that. So here, we're using compile time built-ins. Our previous best thing is kind of the normalized standard now. And it turns out taking and returning a list of U8 is still faster. It's about 6 times faster. And the reason is that the component model requires these various flags to be manipulated around every call. I don't know exactly what flags they are these days because they sort of changed at some point. But they used to be like the may enter and may leave and all of that stuff. And so when you actually look at the disassembly of the adapters that we end up inlining before we inline them, we end up with like an extra load, 2 extra stores, an extra, compare and branch, and then a handful of extra bitwise arithmetic instructions, none of which are actually necessary for what we're doing here. And then additionally, we have that bounds check in the compile time built-in. And crane lift isn't able to deduplicate and lift the bounds check outside of the loop yet. We have plans for doing that eventually and ideas around how to do that, but it's just not implemented yet. And so because of all of those things, when we're touching every single byte in the buffer, copying in and out ends up being cheaper. But what if we're not touching every single byte in the buffer, which is sort of the use case for when you don't want to copy, right? It's like, I'm just going to do a little bit of something here or a little bit of something there, right? So here we're going to benchmark incrementing 1 random byte in the buffer using kind of the zero copy approach with compile time built-ins versus taking and returning a list of U8. And so taking and returning a list of U8 is the benchmark or the, kind of the normalized version here. And so switching to the kind of zero copy host buffer API and still using linker func gives us like a 25x speedup. And then we get another 1.7x faster by switching to compile time built-ins and removing the function call overheads and all of that. So they're ultimately, almost 43 times faster than taking and returning a list. So benchmarking TLDR is compile time built-ins and the zero copy style of APIs are faster than linker func when you have these kind of like fine-grained APIs, like I guess like the zero copy host buffer stuff. And they're also faster than copying data in and out of WASM when you're only accessing kind of a subset of that data. I guess that's sort of the same point. And they're currently slower when you're copying data in and out when you're accessing most of the data. But hopefully that is not the case indefinitely. We sort of have plans for addressing that. So the next steps are the biggest question I have is, I've kind of lost track of exactly what's going on in the component model with all of these flags. And all of these like async and concurrent state checks. Do we really need all of that? Like, is there stuff that we can kind of punt from the component model into user space and guests that want to catch reentrancy or whatever can kind of implement these checks in user space themselves, and then guests that don't need those things don't have to. Because if we can remove all of this, then that's a really easy way to remove these host calls, and then really easy way to remove all of these instance flag stuff. And so all component-to-component calls will get a lot faster, and compile time built-ins in particular will really benefit. If we don't do that, then we've kind of got our work cut out for us. We need some kind of combination of like static analysis at the kind of component, like the way that everything's getting linked up together and the lifting and lowering pairs and all of that. A static analysis to kind of figure out like when exactly which checks can be elided and when they're unnecessary. And this is a little bit tricky because we also don't really know the body of functions at that time, and so we can't test if they're like actually calling out to other stuff or not, at least without like a bunch of refactoring and probably slowing down compilation and translation to Cliff. Also, it's the kind of thing where, if you accidentally tweak something and then the static analysis can't like prove that it's safe to remove the checks anymore, or the checks do become required, then you end up with these like perf cliffs where all of a sudden things get a lot slower. Similarly, we could also try to greatly improve craneless alias analysis to kind of remove those the instance flag manipulation when we can see that like, oh, we like set it and then we did some stuff and then we unset it. Yeah, it's a bit tricky, but like we can probably do it. Could be nice, might slow down compilation in general, and then also sort of maybe has similar issues with the perf cliffs. And then the other thing that I really kind of don't like is adding like a trust me button, saying, hey, I'm the author of these compile time built-ins and I understand the spec, so trust me that these things aren't needed. The problem is that this is a foot gun because maybe it was true that they weren't needed when you initially hit the button, but then, over time you make little patches or whatever, and all of a sudden, oops, it's needed again, but you didn't realize that, so you didn't unhit the button. Or also just like most people probably don't know the spec well enough to be able to like make that nuanced decision of whether it's okay to trust me or not. Yeah, other random things. So we had bounds checks in there, right? We should probably have Spectre guards for those bounds checks and allow people to do that themselves. This probably means adding kind of a fused bounds check and load or store unsafe intrinsic. We might want to add atomic loads and stores, and unsafe intrinsics for doing that. And then, as mentioned earlier, we need to improve Cranev's ability to deduplicate and lift outside of loops bounds checks so that uh, things get faster and nicer. Um, yeah, and then I guess kind of the other thing is, should we push this into WASI? Should we define like a zero copy host buffer interface and resource in WASI? And once we have that, should we have extend WASI HGP, for example, with accessors for getting headers and HTTP bodies and stuff as these zero copy buffers? Um, so that, if you're in a use case where you're like, oh, I'm actually not going to touch the whole thing. I just want to like check a little bit here or there, or do like some random access, whatever, you can do that. So that's everything I have. Questions, discussion.
There were a couple of questions that came through on Zulip that have largely been answered, but I'll give you a chance to speak to them as well.
Hmm.
Um, Yash says, wait, is what Nick is describing made to enable U-ring like direct access to APIs?
I think you could pair this with that kind of thing. I'm not super familiar with U-ring, so I can't really speak to that in too much detail. But it does allow you to share buffers, and then if you have some sort of protocol for when each side touches it and doesn't touch it, it seems like the kind of thing that you could make work.
Cool, cool. Are there more questions from folks? I mean, this is exciting stuff. We've been talking about zero copy in the component model for ages. Till asks, the zero copy buff interface would require host to support compile time built-ins to implement it, right?
No, you can implement it with linker func and in fact, I did earlier. And it can actually still be a benefit depending on, essentially the size of the buffer and the amount of data that's being accessed, right? But compile time built-ins will be faster than than the linker func version. And you can also polyfill it. There's nothing that's like requires anything special from the component model. So you can polyfill it or virtualize it or whatever as well. And of course, like to actually get that data to the host, it would still require a copy in that situation or whatever. But from one WASM component to another WASM component wouldn't require any copies or anything there. Uh, yeah.
To clarify what I mean, I understand that you can implement the semantics described in the interface, but
Mhm.
you can't implement it in a way that justifies the name zero copy buff without being able to inline.
It would still be
Actually,
zero
no.
copy. It just
Yes,
wouldn't be
you're right. It
zero.
would still be. It would just be
Yeah.
slower. Yeah.
Yeah. It wouldn't be zero function overhead.
Yeah.
Dave asks in Zulip, if the component model has a native concept of remote buffers that can be optimized to heck, how much of the overhead remains?
Um, yeah, I guess so. So I just talked about how these things don't require any magic in the component model, like they don't need intrinsics or whatever. But I guess if we did put them in the component model and then added intrinsics for these like get and set operations and the length and everything, then we could just define those things as not um, doing the whatever state management checks or manipulations or instance flag checks, like the may enter, may leave. And so I guess we could sort of like, spec define our way towards all the optimizations in that case, perhaps. Uh, yeah, I don't know. Like from a like PL design perspective, I don't love it. From a like engineering just get it fast perspective, it's kind of tempting.
Luke.
Is let's say in my C code I wanted to like take the address of something that's in one of these buffers and then like pass it to just random C code so I could load and store from it. That wouldn't work, right? Because I need to know at each load and store site that I need to call this import. It's sort of like it's like a multi-memory in a sense, in that I need to
Yeah.
statically discriminate at each load and store site. This one
Yeah.
goes
So
from the buffer versus normal linear memory.
yeah, so in the guest, you can't treat it exactly the same as any other pointer or anything, right? So you could kind of think of it as like cherry or something, right? Where it's like your hidden part of the pointer is like which zero copy host buffer am I doing? And then like your loads and stores
Yeah.
are like doing the special thing.
So if you did
Um,
like a fat pointer, that would be a way
yeah,
to solve it.
exactly.
So then you could say if we wanted to have all of our cake and eat it too by maximally optimizing, there's this idea. It's in Wagner called shared heaps. We've talked about it with the Firefox folks. They sound interested to do some experiments because it solves some browser use cases like how do I map an array buffer into my WASM linear memory. In that case, with that sort of feature, which I won't go into, then we could map a buffer into linear memory. So then it would just, you could load and store from a normal I32 offset. And then it wouldn't require any static distinction between these are the ones in linear memory and these are the ones out of linear memory. And so that's one thing that we could go if we went, and that requires a core WASM change. Uh, and so it'd be beneficial kind of more broadly, but that's one way to do kind of 1 degree better for like I can just take the address of this and then
Yeah.
and call a random C library that just has normal C code and it's just like loading and storing from this, but it happens to be this mapped buffer instead of like normal linear memory.
Yeah, that's true. That does ultimately give you better toolchain UX. Um, I will say there are some asterisks there though, beyond just like the standardization stuff that you mentioned. One is that I think this requires like virtual memory in order to like effectively move things around, right? Like if you want to map in a new thing, you've got to like put it there, or you need like soft MMU or something, right?
Well, the implementation, if this gets into the details of, but if you say there can be at most one mapping, one can do it with a cheap branch. So it's a
Yeah,
software emulation, but it's pretty cheap. What we want to get is the actual exact performance numbers, but at
yeah,
least from what we've heard, it can be quite tolerable. And then
yeah,
if you have an MPU, there are some cases where hardware actually can let you do it without like syscalls or TLB flushes or any of that stuff. So that's the more advanced technique, but it
yeah.
can be at modest overhead without um, touching virtual memory or remapping or flushing TLBs and all that.
I will say our embedding is going to want many of these. Um, and we also don't have virtual memory available. Um,
Well, if it's just updating a pointer, you can change mappings like with a single store. So you can change mappings really fast. It's like I want to touch this one, map,
mm,
touch,
mm,
and then touch this one. So it is with it's not without trade-offs, and I'm not saying it replaces or subsumes what you're talking about here. I'm just saying to the earlier question of if we a thing that would let us go a little farther to have like that real like you know it's just in linear memory, so I can just have a pointer to it. That's a thing that
mhm.
could be then lifted into like a buffer type. That could be a component model, just a WIT type. You can just pass around by unique ownership. So it's transfer in, map it, poke at it, unmap it, pass it away, and
Mhm.
and that would be complementary, I think, for some use cases. Also, it'll take a lot longer. So what you're doing works now, and is great. So
Cool.
Chris says in the Zulip that zero copy buff without inlining is zero copy in a weird sense because it's giving you the U weights one call at a time, the money transfer structuring cheat of the buffering world, which I think that's so beautifully said. Till says, I wonder if lazy lowering could introduce support to lower stream chunks into a zero copy buff like thing as a canon opt. I guess more generally for list of U star as well. Joel
Yeah.
says, again, though, If you can just allocate your buffers from guest memory to begin with and let the host use that directly, no fanciness required, uh, that should be the default choice, in his honest opinion. It does imply magic host powers and isn't virtualizable though.
Yeah, the thing is often the host ends up being forced to do a copy as well. Um, yeah, but when you can, for sure.
Yeah, to that, Till says that requires much more massive change to everything around it, though, and isn't always feasible at all. Alex.
Hey, so I wanted to call out. I think in chat that was happening. There's an issue on Wasmtime for optimizing these async stuff with concurrence and state changes and all that. So I basically wanted to call that out. I think it's let me 12311. That's got a lot of discussion about possible optimizations there in terms of things of refactoring we can do on the async side of things to push more stuff inside of VM context style business. And then additionally, I think it would also remove some of the extra state manipulations that are happening currently. It's also
Yeah.
one where I think we will have to sit down and spend a little bit of time on what exactly all these state manipulations are doing. So some of them are like the async task stuff, but we need to optimize that for other reasons, like stack pointer checks and context getting set. That's all just orthogonal to this. But then there's also the aspect of what am I saying? Like the may enter flags, the may leave flags, like these instant flags that are kind of built into Wasmtime. We will likely have to do some sort of static analysis within Wasmtime on our compilation side to say we don't have to do those. I think it's a little too much to put on Cranelift to optimize those out, but I'm not too worried too much about the perf clips there in the sense that like the shape of compile time built-ins are highly likely to fit inside that bucket, and you have to be doing really weird things inside of compile time built-ins to fall out of that bucket. So I think it'll generally work out. And from the Cranelift side, I think on that issue there was I think one or two minor optimizations we need, such as I think a Cranelift would need to know that if you basically a little bit of dead store or dead load elimination, I forget exactly which, getting rid of those, but those I think are very tractable for Cranelift to do, as opposed to like brand new alias analyses.
Yeah, so right now, Cranelift will eliminate dead loads and replace them with, a use of the, I guess, or well, yeah, we'll eliminate dead loads if they're trusted and won't trap or whatever, and then we'll also replace redundant loads with uses of the previous value. We don't eliminate dead stores because that's a bit harder and that's going to require work. But like, I don't know, it would probably be nice to have anyway. Yeah, I don't have a great sense of how much compile time overhead it might impose though. And I guess like this is kind of opens a question in general, which is like the more sort of stuff like if we're going to do static analyses based on right now we do static analyses at the WASM component level just based on like the linking and everything and the instantiation, right? And then like each function body is still compiled kind of independently. And when we're doing the analysis on the like linking and all of that, we don't know the contents of the function body. So we don't know if it's like going to make any calls or not and is potentially reentrant or whatever, right? But like the more we kind of push on this, like the more maybe it makes sense to like actually inspect the WASM body at that first initial static analysis time, if that's going to give us better results or whatever, right? But then how much is that going to impose to compile time overhead? And like, do we want to like have an O3 or something now or what, right? Like, I don't know. There's like, I feel like there's a whole discussion around like, how much do we want to push the architecture towards like more, better code gen and worse compile times. Obviously, like limiting that as much as we can, but yeah, there's a conversation to be had there.
I definitely agree with that. And in my mind, the goal is to get to the point that a sync to sync, component to component call, which is what's happening here, had literally zero instructions of overhead. And so I think, I personally, I think we should definitely be able to get there. But we'll have to figure out how exactly.
Also, did we already even remove kind of with the spec changes at compile time the recursion check for component to component calls already?
We did, yeah. That we kind of went. There was a bit of a back and forth where we kind of went. We took, I think, one step forward, and then we took one step backward in terms of costs involved there. So we like removed stuff, or we added stuff, then we removed other stuff that ended up being similar costs. But yeah, so those are gone. We still have a couple of other minor things, which honestly might just be outdated, and we can go back and like statically remove those as well. we haven't really given them a whole lot of thought. And so it might not, all the static analysis may not even be necessary. The component model changes might be sufficient for removing some of these flags. We just haven't revisited them.
Yeah. I have tried to look at the component model spec to find all of the flags and like sort of their motivation, and I've come away like not having found them. So it would be really useful to like have a place where we have kind of like compiled, here's like everything that an adapter must do, and like here's the motivation for why also. Because like that's my next question, right? Is like, okay, I have to do this. Like, do I really have to? Like, can we not? So I don't know. That would be really helpful for me, but I also see, that's work for someone to do.
Well, I would say that I think the document you're looking for used to be the component model spec, and then the spec changed, and we haven't caught up in Wasmtime. So I think that's just a lot of some catching up work to do there.
We've got another question from Dave. How optimized is the current async state transition stuff? Is it at a first implementation level that satisfies the spec as cleanly as possible, that is optimized for spec compliance rather than performance, or is it already optimized decently? Given the huge difference in bar heights on the graph, I'm just trying to understand if the big bar is just an effect of the current implementation or it's necessary by design.
I'll take this if you want, Nick.
Yeah.
I would describe it as what's necessary to satisfy the spec currently. So it's not heavily optimized, and I think it contributes to the very large bar. What Nick was showing before concurrency support was disabled, that is sort of what you would see right now. It's a little bit worse for if you call it async function. So Nick's doing the absolute optimal case from a static point of view of a synchronously typed wit function is synchronously lowered and synchronously lifted, and all of that's being fused together, all synced, no async whatsoever. And even that is still this exactly we got, well, I think this 3.5 times slower. Once you start adding async to the mix, so async lowerings, async types, things like that, it gets a little bit slower as well, in the sense that we have to manage some fiber stuff. We call out for the host for doing a little bit more heavyweight operations. So that'll definitely need some work over time. But I don't think that would affect this compile times built-in work, in the sense that unless it seems, at least in my mind, it would be pretty unlikely you're writing an async compile time built-in. And while it is possible for a component to async lower your compile time built-in, the expectation that would be fast is not really on the table. It's fine. It just works as opposed to being the fastest thing possible.
All right, we got any other questions?
Also, just add, I think a big part of that big delta was those host calls. I mean, adding a host call in a very hot path is going to dominate. I think they've been eliminated by design now. Like that was a spec level change that motivated that killed those by design in component to component calls. So even though there's still more work to do, I think the biggest, fattest part of that has already been lopped off. Is that right?
I would describe it as kind of two halves. One was we did require some for the reentrancy checks to host calls, and that has now gone at the spec level and has gone at the translation layer, and that's why if you disable the concurrency, it goes away. We have the other half though of managing the async task stuff, in the sense that we still have to call out to the host for that, and that's not gone from the spec level. And that part is the one where we have an issue about optimizing that and making it so we move all of the task manipulation into the trampoline, and all of that can be very easily rolled away by crane lift.
Yeah, I think there's sort of two layers. It's like first you have to like get it out of the VM and into the inline trampolines, and then we can optimize it. And that can probably remove a bunch of it, but probably not everything on its own, right? And then there's like the static analyses to like, let's not even emit code to do whatever flag if we don't need to, right? And for that latter part, the static analyses, I think it would be also really useful to like get precise preconditions for when we can alive things or not, because that also seems like something that's somewhat ambiguous in my mind, at least.
Yeah, that one I think we definitely need to sit down and kind of just do a little bit more thinking on the Wasmtime side of, do we, like exactly what you're saying, of do we even still need this, and then I don't think I do think that's a separate bucket from the async task manipulation, but I think it's definitely tractable.
Cool. Anything else?
Which, we've taken a lot of questions and comments. I haven't heard any concerns from anyone. Someone throw in a concern. Going once? Twice?
I'm deeply concerned about how fast this is going to be when it all works.
Oh, yes. Deeply concerning. Excellent. Well, thank you so much, Nick. That was absolutely riveting.